Lecture 9, Part B, on rotational motion. Recall in Lecture 9, Part A, we made the analogies of torque as rotational force, moment of inertia as rotational mass, angular acceleration, and Newton's second law in rotational form. Angular acceleration results from a torque divided by the moment of inertia. Here we have an object that's moving and rotating. If we wanted to, say, look at a piece of the object and see the path that it makes, such as the end, we see the end of the screwdriver is making a nice, pretty, but complicated path. If we want to look at that path and analyze that path and to figure out the motion of that path, which is a motion diagram, it'd be quite difficult to figure out the accelerations and the masses and the forces and talk about the torques and the moment of inertia by analyzing that path. What we can do, though, is simplify by knowing some physics. If we follow the center of mass of our object, we see the screwdriver rotates about its center of mass. And the center of mass follows a simple path, a parabola. This is the same motion, the same path that a ball would have if thrown with the same initial speed. The center of mass of the screwdriver follows the path of a thrown ball. It's ballistics. We divide the motion of that screwdriver into its rotational motion about its center of mass and the translational motion of the center of mass. You translate from one language to another. Physics, we translate from one position to another. Translational motion, the object as a whole moves along a trajectory but does not rotate. Rotational motion, the object rotates about a fixed point, its center of mass. Every point in the object moves in a circle. The combination of these two, object rotates as it moves along a trajectory. The rotation about the center of mass. Here we see two dumbbells, two heavy bells connected by a long rod. Which of these dumbbells will be easier to stop or stop rotating? Will the top one be easier to start rotating or stop rotating? Will the bottom one be easier to start or stop rotating? If you swing these two dumbbells, if you were to stop them by getting hit, which would be harder, which would hurt more? If they hit you, and that stops the motion. Clearly the bottom dumbbell, with the heavier bells, if that one was to be rotating, it would hurt more if it hit you. The greater the mass is, the farther they are apart, the more difficult it is to get the object to rotate, and likewise the more difficult it is to stop the object from rotating. We can think of the top dumbbell as like two sledgehammers connected. We can think of the bottom dumbbell like two larger, longer sledgehammers connected. It's very hard to swing a sledgehammer from its end. It's very hard to swing these two dumbbells far away from the center of rotation. This is again the idea that we continuing on from in Lecture 9a about moment of inertia, the rotational mass. The I, moment of inertia, rotational mass, depends on the amount of mass, the dumbbells, and how far the masses are from the center of rotation. More mass and the farther they are, the harder something is to rotate, like the kids sitting at the end of the merry-go-round. The kids come in to the center of rotation of the merry-go-round. The masses closer in are easier to rotate, easier to start and stop rotating. So similar to inertia, mass, for linear motion, the reluctancy of an object to change its motion, speed up, slow down, or change direction. Rotational inertia, the rotational mass, I, depends on the mass, but it depends on how the mass is distributed with respect to the axis of rotation. Rotational inertia increases with an increasing distance the bulk of the mass is from the axis of rotation. A wheel with a bulky tire has a greater tendency to remain rotating than if the mass were near the center. So if you have a number of particles in a rotating system, to find the moment of inertia of the system, you simply add up the particles' moment of inertia. Add up the values of I for each object. For example, we can break the dumbbell into two sledgehammers. calling them I1 for dumbbell 1 and I2, a distance 1 and a distance 2, the same distance from the center of rotation. So I1 plus I2 is equal to the total moment of inertia. I1 is the mass of dumbbell 1 and the distance dumbbell 1 is from the center of rotation squared. Likewise, the same mass M2, the same distance D2 squared is my I total. For I3 and I4, it's the same principle. Increase the mass, but more importantly, as you increase the distance, D3 and D4, that distance gets squared and has the more dramatic effect. It's harder to get the second dumbbell, the bottom dumbbell, to rotate as a greater rotational mass, rotational inertia, or moment of inertia. Not so much because the masses are greater, because the masses are farther away from the center of rotation, which has the greater effect as it goes as d squared, the d being the center, the position vector from the center of rotation to where the masses are. A shape can have a different value for I depending on the axis that it's rotated about. For example, our dumbbells can be rotated about the center or rotated about an edge. Which is the greater value of I? The dumbbell rotated about an end or about its midpoint? We can look at the equation for the moment of inertia, the total moment of inertia. And the equation would be the mass of each bell, the distance each bell is from the rotation point, from the pivot, from the end of the dumbbells, or from the midpoint, from the center. The dumbbells are rotating about the center or the end. We simply add up the values and we'd see that the dumbbell rotating about its edge, or about an end, is harder to rotate than about the center. Why? The masses are the same for both the left and right scenarios. The difference is the distances from the pivot points. The distance in the pivot points when rotated about the center is simply half the length. The distance from the pivot points, the end of the dumbbell, to where the masses are for the left example. The first distance, d1, is less, but the second distance, d2, is twice the length. Because the distance is the most important factor in the moment of inertia, since it gets squared, the object that has the greatest distance, dumbbell 2 in the scenario 1, has a dramatic effect in increasing the moment of inertia. The mass times d2 squared in scenario 1 is a much greater contribution to the moment of inertia than the dumbbells are in scenario 2, rotated about its midpoint. It's harder to rotate the mass farther away from the center of rotation, so it's harder to rotate the dumbbells in this scenario to the left. It's the same thing as swinging a sledgehammer or lifting a sledgehammer from an edge, from the far end, versus near the hammer. It's not so much because the weight of the sledgehammer is great, it's the distance from the weight, from the hammer, is great. Different objects have different moments of inertia. Their formulas we see here all depend on the mass of the object, and R, the distance of the mass, the shape of the mass, whether it's the length, whether it's the width of the rectangle, the radius of the disc, or the radius of the cylinder, or the radius of the hoop. It's all about mass being distributed over some distance from the center of rotation. So a rod about its center, like a dumbbell about its center, has a particular moment of inertia. And a rod about its end has a greater moment of inertia, with the same mass swinging about one end, because the distance, how the mass is distributed away from the center of rotation, away from the rotation point, is important. So in a rod about its center, it's 1/12 ml squared. A rod about its end is 4 times greater, 1/3 versus 1/12. The same mass times the same length squared. The coefficient 1/12 versus 1/3 depends on the shape, which comes from integration, which we will practice in homework problems, in worked out examples, and in the IL. The shapes of the rectangles, being swung about their center or swung about their edge, follow the same principle as the rods. The rectangular shape is like a whole bunch of rods stacked along the length B. Again, we get 1/12 and 1/3 times the width of the door rather than the length of the rod, A. Rotating a cylinder versus rotating a hoop. Rotating the cylinder is easier than rotating the hoop. 1/2 mr squared versus rotating the hoop, the full mr squared. Why does the cylinder have half the moment of inertia, half the rotational mass? Because much more mass of the cylinder or the disc is located close to the center, whereas for the hoop, all the mass is as far away as possible. The same is true for the hollow sphere versus the solid sphere. More mass is closer to the center of rotation for the solid sphere. For the hollow sphere or the shell, more mass, all the mass is at the edge, the farthest it can be from the center of rotation, which makes it harder to swing. 2/5 versus 2/3. We can find the center of mass of the dumbbells or any object by a similar method, locating the masses and the distance the masses are from the center of rotation. So the distance of COM, the distance of the center of mass, is the mass times its distance d1 from the center of rotation, plus the other mass of the bell, m2, times the distance 2 that it is from the center of rotation, the edge of the dumbbell, divided by m1 plus m2, the total mass. So it's simply the product of the mass and its location from the pivot. Simplifying, if the masses of the bells are the same, if m2 equals m1, then the total mass is 2m. Therefore, the masses cancel out, and we're left with the distance of the center of mass is d1 plus d2 divided by 2. d1 plus d2 is the total length of the dumbbell, divided by 2 locates the center of mass at the midpoint of the dumbbell, exactly where you'd expect it if the bells are of equal mass. If I rotate the dumbbell about its center and I use the same equation to figure out the center of mass, I should get the same result of the midpoint as the center of mass. And I do. dCOM, the distance to the center of mass, is m1 times d1 and m2 times d2. The difference in this case is d1, the distance of the left dumbbell, would be in the negative direction, where the distance to the right dumbbell is to the right of the center of the pivot, which we would call the positive direction. Their position vectors are opposite directions, so we throw a negative sign there, m1 times negative d1 plus m2 times positive d2. Makes the two terms m1 d1, m2 d2, if the masses are the same, then the terms cancel out and the distance center of mass is 0. Right down the midpoint. If the masses are different, if the mass of d2 of dumbbell 2 is much greater, then we expect the center of mass to be much closer to dumbbell 2. Again, looking at our equation, m1 d1 plus m2 d2 divided by the total mass m1 plus m2. Let's say our mass of dumbbell 2 is 5 times as great as the mass of 1. So therefore, our total mass is 6 times the mass of 1. Let's say the distance 2, we know how much greater distance 2 is versus distance 1. Let's say distance 2, canceling out the masses. Let's say the distance 2 is 4 times the distance of 1. Then distance 1 plus 5 times 4 times distance 1 again is a simplification of our terms divided by 6, which gives us 21/6 times the distance 1, or 3.5 times the distance 1, is where the center of mass is located. The center of mass is not halfway. The center of mass is 3.5 times the distance. 3.5 times distance 1, the center of mass of the first dumbbell. 3.5, the distance 1, puts the center of mass of this overall system much closer to dumbbell 2, as expected. Our equation with an integration is very similar. X times dm is simply saying x, the location of each chunk, infinitesimal chunk dm, of the masses. We sum them, as we did before, but we sum an infinite amount of infinitesimals. We integrate the location of the masses divided by the total mass. In worked out examples, and in homework, and in IL, we'll do examples of center of mass calculations. Center of mass for an object that's not a rod or a triangle, such as a body, we can do exactly the same principle. We can find the center of mass of each limb in a variety of methods. The center of mass of the overall body is adding the locations of the center of mass of each limb. The distance from the center of mass of each limb to the pivot point, in this case her hands, those distances and those masses added up gives the center of mass of the overall body located in the woman's hips. This is where the weight of the force of the earth acts on all objects at the center of mass. A rotating object also has rotational energy, such as all the atoms in the object have kinetic energy of 1/2 mv squared. The net kinetic energy is adding up to summing up all the atoms, all the parts of the body, 1/2 mv squared. We sum all those guys up. Those are tangential velocities. Since the mass is rotating around, if an object is rotating, then all the little masses of all the little atoms are rotating about with tangential velocity, and tangential velocity is r omega. So 1/2 mv squared, 1/2 mv tangential squared is equal to 1/2 m r squared omega squared. If the whole object rotates as 1, then all particles are the same omega. So 1/2 sigma, adding up all the masses and the distance of the masses are, mr squared times omega, gives us the simplification 1/2 I times omega squared, because sigma mr squared is rotational mass moment of inertia. So 1/2 I omega squared is the rotational kinetic energy. Just as kinetic energy translational is 1/2 mv squared, kinetic energy rotational is 1/2 rotational mass times rotational velocity squared, 1/2 I omega squared. It's nothing new. We just call this form kinetic energy rotational. Let's do some examples. A high-speed drill rotating counterclockwise takes 2.5 seconds to speed up from no rotation to 2,400 rotations per minute, RPMs. What is the drill's angular acceleration? The angular acceleration of the drill is how much it's changed its rotational speed, its rotational velocity, omega. Its initial rotational speed, omega initial, is 0. Omega final got up to 2.5 seconds, got it up to 2,400 RPMs in 2.5 seconds. So omega final is 2,400 rotations per minute. What's a rotation? A rotation is 2 pi. A full circle is 2 pi radians in one rotation per minute, 60 seconds. Alpha, the angular acceleration, is a change in omega and a change in time. The change in omega, the angle swept, delta theta, is omega average times delta t. Or what is omega? Omega is delta theta divided by delta t. This is our average omega, not an instantaneous value. So 2 pi n times omega final divided by 2, because omega average is half the final, and delta omega is equal to omega final. So the angle swept delta theta, how many rotations? 2 pi. How many n 2 pi's, how many n rotations, is equal to omega average, which is omega final divided by 2, which is the 2,400 RPMs divided by 2, times the time of 2.5 seconds. Now you know how to solve for the angular acceleration alpha, and the value of n, how many rotations does it make as it reaches this final speed. You can complete this solution on Blackboard. An object, a rope over a pulley that's being pulled by an object to rotate the pulley, is another example of using rotational energy and torque with the rotational variables that we've learned in this lecture and the previous lecture, this chapter and the last. But we can make a connection. As the rectangular object, pulls on the rope to spin the pulley, the acceleration and the velocity of the object must be the same as the acceleration and velocity of the rope. Otherwise, the rope would separate or squish together or do something else. But if the system moves as a whole, The velocity of the object and the acceleration of the object are the same as the velocity and acceleration of the rope, which therefore is the same as the velocity of the rim of the wheel and the acceleration of the rim of the wheel. So velocity is equal to the velocity of the object at the rim is equal to the rotational or tangential velocity, omega times r. So v of the object is equal to omega times r, and the acceleration of the object relates to the rotational acceleration alpha. So r times alpha is equal to acceleration of the object. These are connections between the motion of the block and the motion of the pulley. The rotational motion directly linked to the translational motion. So, how long does it take the small mass to fall 1 meter when released from rest? Using our knowledge from the previous slide, we can connect the rotation of the pulley to its velocity and acceleration at its rim to be the same as the velocity and acceleration of the object as it falls. And we can use the knowledge of energy conservation. The loss in gravitational energy of the object as it falls relates to the rotational energy of the pulley. So we know that the curve, the distance of the pulley as it's rotating, r times delta theta, delta s, is equal to how much the rope has unfurled from the rotation. So how much the object has fallen, delta y, relates to the length of rope that has come from the pulley, that the pulley has rotated, which is related to the amount of the distance of rotation, r times delta theta. So the rope that comes from the pulley, the delta y as it descends, is the same as r times delta theta. Therefore, delta theta is equal to delta y divided by r. The loss in gravitational energy of the object as it's falling is equal to the increase in kinetic energy. The object is falling to make the pulley rotate, is what this means. mg negative, the loss in PE gravity, negative mg delta y, is equals to 1/2 I omega squared. Gravitational energy and kinetic energy. The negative signs for the loss of energy and the loss of height, negative delta y, cancel out. So all our equation balances in signs. I is equal to mr squared times delta omega squared. Rearranging the terms, 2mg delta y mr squared times delta omega squared. Delta omega squared, again, is delta theta divided by delta t. Taking the square root, we can rearrange to solve for the time, for how long it takes. There is an error in this calculation that I embarrassingly just caught. The I, for the moment of inertia, the rotational mass of the rotating pulley, is 1/2 mr squared. So there's a missing 1/2 there. So it should be 1/2 times another 1/2 mr squared times delta omega squared. So include that extra 1/2 in the moment of inertia I for a disc or a pulley, as we saw in a few slides back. There's an extra 1/2 on the term on the right. That should be included in the overall solution. Complete this solution with the values given on Blackboard. Don't forget the extra 1/2 term. Simplifying, taking in what delta theta is equal to, delta y over delta r, we now know we're given the value of delta y, we're given the value of r, we're given the masses, big M and little m, and therefore everything is known. And make sure to include that extra 1/2. We can solve for the time that's asked for. The great race, allowing different objects to rotate down a ramp, an activity we will do in the ill. A particle, a sphere, a cylinder, and a hoop all roll down a ramp at the same exact incline, the same exact initial conditions. They all start from rest and are released from the same height. Which one will win the race? Well, gravity affects all these objects to pull them down, where the gravitational energy changes of each one of these objects will be the same. They both descend the same height h. Even if they're the same masses or different masses, it won't come into effect, as you will learn, and you will discover in the L. What we have to consider here is which objects are easier to rotate. An object that's easier to rotate takes less energy to rotate, and therefore less kinetic energy of rotation, and more kinetic energy of translation. So the loss in gravitational energy goes into two new forms, two new energy tanks. It goes into rotational energy and translational energy. The one that's easier to rotate will have a greater change in speed. The one that's harder to rotate will take more energy from the gravitational energy loss. Will be put into rotating the object and less into speeding up the object. So consider which one of these objects is the hardest and easiest to rotate. Then you can figure out which one finishes first or last. We can make again some connections. The velocity of the center of mass of any of these objects, such as the ball and the hoop, relates to r times omega. Why? Because after let's say this circle here, this disk, makes one full rotation, it covers a distance of 2 pi, r. The speed, velocity of the center of mass, is distance per time. So after one full rotation, it's covered a distance of 2 pi r on the ground in the time frame of one full rotation. So 2 pi r divided by the time is the same thing as 2 pi over the time. The angle over time is omega. So 2 pi r over time is the same thing as r times omega. And again, the kinetic energy of an object that's rotating and it's moving is kinetic energy rotational, kinetic energy of the center of mass, or translational. So the objects that have their masses concentrated close to the center have lesser values of the coefficient for the rotational mass, and thus take less energy to rotate and more energy for the center of mass to translate or move down the ramp. Look for the full solutions in your textbook, and you will work them out with the actual data and values in the L. Again, returning to Archimedes, who we mentioned in Lecture 9a, Archimedes was an ancient Greek living right before the Roman Empire took over the island of Sicily, where his Greek city-state was located, Syracuse. Syracuse was a fortified city, whose fortifications greatly increased under Archimedes, as the local king or tyrant employed Archimedes to create machines, levers, and pulleys of various sorts to defend the city from the attacking Romans. Late in his life, when the Romans laid siege to the city of Syracuse, the Romans supposedly would stay at quite a distance away from the walls of Syracuse because of all the machines that Archimedes cooked up, using long levers to fling rocks and to fling objects at the ships, and to use pulleys and grappling hooks of various sorts to capture the ships and tip them over, and to open up holes in the walls. And out comes with strange machines that would grab onto soldiers and smack them against the walls. They were quite fearful of all the machines that Archimedes developed, mostly using their knowledge of levers, leverage, and torque to create rotations of ships and to create rotations to flinging objects. Here's an animation showing something similar. Here's the concept of a leverage from a pulley system and a great force applied to tip over ships. Here's another illustration found on the internet, tipping over a ship from another large leverage system. And here's another one using a grappling hook, a hook tossed to tip over a ship, where the one end of the center of mass of the large object is tipping back and forth until the ship tips over. Some questions to think about for you to pause as we reach the end of this lecture.